I will define new topic, new space, metric space. This is actually very useful and very fundamental topic in mathematics. Today I will define how metric related to function, vectors, all these things. Actually metric be a pair where X be any vector space, function space and D is the distance which is denoted as metric. Metric space means actually distance of a function. At first I will say how mathematically define distance of any two vector. Mathematically actually the metric space is a set such that for every x on the set capital A, we can define distance between 2 points x and y, which is actually denoted as d of xy, which is actually distance between these 2 points. And this distance function is called as metric, which satisfy 4 criteria. It cannot be negative. Distance function always greater than equal to 0. As for example, if you consider 2 point minus 5 and minus 3, then their distance be obviously minus 2. But here this indicate distance function always greater than 0. So we have to find distance absolute value. So their distance would be plus 2. Because distance function always greater than 0. Here distance between x and y equal to 0 always imply x equal to y. Third condition, distance is always independent of direction. Distance between x and y always same as distance between y and x. That means distance from x to y always same distance from y to x. Okay? So actually distance is independent of direction. Next property is triangle inequality. Here triangle inequality must be whole. If you look the picture, if you consider 3 arbitrary points x, y and z, then distance between x and z always less than equal to distance between x, y plus distance between y, z. Okay? These 4 properties always hold for metric space. So actual definition of metric space is, the definition is, consider x be a non-empty set, then D, which is denoted as distance function. This is mapping from x cross x to close 0 infinity, and the mapping is such type x comma y map to distance of x comma y, and the properties are d of xy always greater than equal to 0 and 0 if x equal to y. This condition is if and only if condition. If x equal to y, then obviously d of xy equal to 0 and distance between xy always same as distance between yx. This is the symmetry property. And triangle inequality, distance between x and y less than equal to distance between xz plus distance between zy. And obviously for all x, y, z belongs to this non-empty set x. This is the definition of metric space. No, okay. Norm means length of any vector and metric space means distance between two vectors. Actually every non-linear space always metric space, but converse does not true always. Let's see the proof. Consider the metric space as D and D be a mapping from n cross n to R, and here n is actually normal linear space and R means whole real number. That means every pair comes from any normal linear space. and the metric space means mapping here defined as d of x comma y equal to norm of x minus y, where for all xy belongs to R. This is obviously always metric space. First property, d of xy, which is equal to norm of x minus y, by the property of norm, this is obviously always greater than equal to 0. Also by definition of norm, we can tell d of xy equal to 0 when x equal to y. Now d of xy equal to norm of x minus y. Now take negative sign, then this would be norm of y minus x, and obviously this is equal to, since norm function is always greater than equal to 0, that means this is equal to actually norm of y minus x, which is equal to d of yx. That means symmetry property also has satisfied here. Now I will apply triangle inequality. D of x comma z equal to norm of x minus z. Then we can write this as norm of x minus z plus y minus y. Okay. Since norm function is symmetry, so we can write this as norm of x minus y plus y minus z. And by triangle inequality, this is less than equal to norm of x minus y plus norm of y minus z. Okay. And norm of x minus y means d of x with y, and norm of y minus z means d of y with z. That means I have got one relation, d of x with z less than equal to d of xy, x with z plus d of y with z. That means triangle inequality has satisfied here. All condition of metric space has satisfied here. So every nonlinear space are actually be metric space. Are you getting? But converse always does not true, which I will prove few minutes later by one example. If we consider as for example Rn or Cn, then there exists two norm, P norm, which is, we all of us know, summation I equal to 1 to n xi to the power p to the power 1 over p, where p greater than equal to 1 less than infinity, and when p equal to infinity, then this is equal to max I, absolute value of xj. And these two norm always induced a metric space, and this metric space is such type dp x with y equal to norm of y minus xp, which is equal to actually summation I equal to 1 to n absolute value of yi minus xi to the power p to the power 1 over p when p less than infinity, and when p equal to infinity, then this is actually max I yi minus xi. Okay, are you getting? That means consider p equal to 2 and the space is R2, then d of x1 comma y1 x2 comma y2 is square root of x2 minus x1 whole square plus y2 minus y1 whole square. And this is actually nothing but this is actually Euclidean matrix, because this metric is induced by the norm, Euclidean norm, and this is the actual picture. Consider the point here x1 y1 and consider the point x2 y2, and this is actually the distance of this metric. Okay, consider x1 y1 as alpha and x2 y2 as beta. Then obviously this will satisfy first property, this distance always greater than equal to 0, and when these points are same, then this distance is actually equal to 0, and obviously this distance is symmetry. D of alpha beta is always equal to d of beta alpha. For triangle inequality, consider new point x3, y3 and consider this point as a gamma, then this would be just picture, and consider here this point alpha, this point beta and gamma. If we consider this triangle, obviously this distance always less than equal to this distance by triangle inequality. That means this fourth condition also will be satisfied. So obviously this is a metric space. In R2, consider D infinity matrix. That means when P equal to infinity, then this matrix is denoted as D infinity, and the matrix is defined as D infinity xy equal to maximum absolute value of x1 minus y1 comma absolute value of x2 minus y2, where x equal to x1 x2 and y equal to y1 y2, where for all xy belongs to R2. Now show that D is a metric on R2. Obviously D is a metric on R2 because obviously absolute value of x1 minus y1 greater than equal to 0 and absolute value of x2 minus y2 greater than equal to 0. That means maximum of absolute value of x1 minus y1 comma absolute value of x2 minus y2 always greater than equal to 0. That means first condition always has satisfied. Second condition, d of xy equal to 0 means that indicate maximum of the set x1 minus y1 comma x2 minus y2 0. Since here absolute value of this two number, that means these are both non-negative and maximum of two number is equal to 0. That means obviously absolute value of x1 minus y1 equal to 0 and absolute value of x2 minus y2 equal to 0. And these imply obviously x1 equal to y1 and x2 equal to y2. That means d of xy equal to 0 imply x1 comma x2, y1 comma y2 equal to 0 0. And since this condition is even only if condition, then conversely when these 2 points are same, then that imply obviously this distance always same. Third condition also will be true. D of xy always similar to d of yx. Now we have to prove the triangle inequality. This is obviously always true. We have to prove d infinity x comma z less than equal to d infinity xy plus d infinity yz when x equal to x1 comma x2, y equal to y1 comma y2 and z equal to z1 comma z2, where for all xyz belongs to R2. And d infinity x comma z means actually absolute value of maximum of x minus z, okay? And if a set A contains finite number, then maximum of A means if the maximum value is alpha, then maximum of A means this is less than equal to alpha for all I. Obviously, we can write x minus z as x minus y plus y minus z, and this is obviously less than equal to x minus y plus y minus z, and obviously this is also less than equal to maximum of x minus y plus maximum of y minus z. That means triangle inequality here obviously will be true. So obviously d infinity is a metric on R2. I hope my all viewers have understood how we have to find metric on. If I consider space as a real number, then obviously d of xy equal to absolute value x minus y, where for all xy belongs to R be the standard metric in R. Okay, then consider this metric as a D1. Now consider another metric who is considered as D2, who is defined same as before, R cross R to R, such that here the notation is D2 xy equal to absolute value of x square minus y square for all xy belongs to real number. Now my question, is D2 is metric space? Let us verify it. Consider 2 point 3 and minus 3 and notice absolute value of 3 square, obviously minus 3 square equal to always equal to 0, but 3 not equal to minus 3. So D2 is not metric on R. Are you getting? Well, now on R, defined another matrix which is denoted as D3, such that D3x with y equal to absolute value of x cube minus y cube, where for all xy belongs to real number. Now my question, is D3 is metric on R? I will leave it for all my viewers. This is always be a metric space. The answer is yes. Just check it own self. Then I will leave also one another exercise for all my viewers. D4, which be a metric from R cross R to R, as defined as D4x with y equal to absolute value of x to the power n minus y to the power n, where for all xy belongs to R. Then this is the question, for which value of n D4 is a metric space. Just check it own self. These type of question are very important for any competitive exam. I have defined another metric space D5, which is defined from R cross R to R, and mapping is defined as D5x with y equal to absolute value of x plus absolute value of y, where for all xy belongs to real number. Is D5 is metric space? This is very interesting. I will check it. Notice, obviously D5xy always greater than equal to 0 for all xy belongs to R, because this is absolute value of x plus absolute value of y. Then second condition, D5xy equal to 0. That means modulus of x plus modulus of y equal to 0, and this sum always equal to 0 when modulus of x equal to 0 and modulus of y equal to 0. That means, this means x equal to 0 and y equal to 0. But this condition is if and only if condition. When distance between 2 points equal to 0, that implies this point or this equal. Conversely, we can tell if 2 points are equal, then obviously their distance always equal to 0. For this, consider two equal points, x equal to 1 and y equal to 1. Now find d5xy. This is equal to 1 plus 1 equal to 2, which is greater than 0, not equal to 0. That means our condition has broken here. Here I have considered two equal points, but I have got their distance greater than 0. That means our given matrix is not a metric space. Are you getting? Now I will define different type of metric space. Discrete metric space. And the metric is defined as X be any non-empty set. D of xy here defined as 0 only when x equal to 1 and 1 when x not equal to y. And obviously this is metric space because this distance function always greater than 0, so condition 1 has satisfied, and equal to 0 when x equal to 1. Also when x equal to y, then distance is equal to 0, so then second condition also satisfied. And obviously d of xy equal to d of yx. Then next condition is triangle inequality. For this, consider 3 arbitrary point x, y, z belongs to the metric space X. Then d of x comma z always less than equal to d of x comma y plus d of y comma z. We have to prove this. At first consider x equal to z. Then obviously d of x comma z equal to 0. And this is always less than equal to d of x comma z plus d of z comma y, because here the positive quantity. And case 2, when x not equal to z. Obviously d of x with z would be 1, and this can be at first either d of xz equal to 0 or d of yz equal to 0. Then obviously this triangle inequality has satisfied, because when either one of them be 0, then other would be 1. That means obviously this would be 1 equal to 1. And when d of xz and d of yz both not equal to 0, that means this sum would be 2. So obviously 1 less than equal to d of x comma z plus d of z comma y. Means triangle inequality has satisfied here. So all condition of metric space has satisfied here. So obviously this is B metric space. And till now I have seen such matrix who is induced by norm. But this discrete matrix does not induced by norm. This is metric space but not non-linear space, because non-linear space means norm define the length of vector here, and metric define only the distance. Here defined distance of two vector but does not define the length. So discrete metric is not induced by norm. Today I will stop here. In my next video I will discuss this topic also elaborately with more examples. This lecture is just basic, but at first I will highly recommend you please see today's video with pay attention. And if you have any queries about today's video, please do comments in comments box. See you soon. Stay safe and stay positive always. And don't forget to do subscribe for videos.